This video demonstrates several methods to open the CPU's diagnostics buffer. The first method is to highlight your station in Siemens Manager and select the PLC menu. Choose Diagnostics setting. Then select Module Information. When the Module Information tool opens, select the Diagnostics Buffer tab. Let's observe a second way to get to the diagnostics buffer. You must be parked at the station level or below in your project. Then press and hold the Control key plus the D key. This opens up the CPU's Module Information tool. Then select the Diagnostics Buffer tab. Let's see a third way to get to the Diagnostics Buffer tab. Right-click on the Blocks folder from your Siemens project. Select PLC and choose Module Information. Then select the Diagnostics Buffer tab. Next, let's see how to get to the Diagnostics Buffer from the Hardware Configuration Editor. Select your station. Double-click Hardware. In the Hardware Configuration Editor, you must first highlight the CPU, then select the PLC menu. Choose Module Information, and then the Diagnostics Buffer tab. And now we will observe one final method. Close the Hardware Editor. From the Blocks folder, we will open a block. How about FC14? Inside the Programming Editor, select the PLC menu. Choose Module Information, and from here you can access the Diagnostics Buffer. In this video, you have seen methods to access the Diagnostics Buffer from Siemens Manager, from the Hardware Configuration Editor, and from the Programming Editor. See the other videos on interpreting diagnostic messages for more information. This concludes methods to open the CPU's Diagnostics Buffer.
In this video, you will see how to troubleshoot a PROFIBUS station that is down. In the Hardware Configuration Editor, click the Online button. Placing the hardware configuration online shows a graphical representation of where problems exist. In the Online view, double-click the CPU to open the Module Information tool. Click on the Diagnostics Buffer tab. Message 1 shows that the CPU is in stop mode because of a rack failure. Let's click on Message 2. Message 2 says that the distributed I/O station is failed. In the Details window, the DP station that went down is number 4 and is part of the PROFIBUS Master System 1. Close the Module Information tool. Let's take a look at Station Diagnostics. To open its Module Information tool, double-click on the IM151-1 with PROFIBUS address number 4. On the General tab, we see that the module is not available, which agrees with what we see graphically. Click the DP Slave Diagnostics tab. This shows us that the station is not accessible by means of the bus, that is, PROFIBUS. We will now do a physical inspection of the system to see if we can determine what's wrong. It could be a PROFIBUS cable, a connector, a failed interface module, no power to the interface module, or something else. After inspection, it was determined that the wires in the PROFIBUS connector to the ET200S station were not making a solid connection. The cable was trim, the wire newly stripped with a PROFIBUS cable strip tool, and a new connector put on the cable. After the problem was fixed, the CPU was switched to stop and back to run. The station is now up. To refresh the window, press the F5 key. All faults are now cleared. Here is a second case scenario where the PROFIBUS station is down like before, but this time OB86 was created and downloaded to the PLC. Double-click the CPU to open the Module Information tool. Click on the Diagnostic Buffer tab. Now you can see that the CPU is still in the run mode because OB86, the organization block that protects against rack failures, was downloaded. The first message shows that it is station 4 that is down. When the problem is fixed, the station immediately comes back up and all faults are cleared without having to switch the CPU to stop and back to run. To refresh the hardware online configuration editor, press F5. In this video, you saw an example of troubleshooting a PROFIBUS station that is down, and the difference between how the CPU acts without OB86 loaded and with OB86 loaded to the CPU. This concludes the video on troubleshooting a PROFIBUS station.
In this video, we will review the System Detected or Stop Error category and some of the tools used for troubleshooting them. At the top level, there are basically two categories for errors. Those that the system can detect, sometimes called stop errors, and those that the system cannot detect, called functional errors. System detected errors will usually cause the CPU to go to the stop mode if there's no organization block protection. With functional errors, something doesn't work right, but the system cannot detect what it is, and the CPU does not stop. The first category we will look at is stop errors. Some examples are hardware or communication failures, a wire break on an analog module, a program scan time overrun, or forgetting to download a block causing a block not loaded error. Here are the typical tools used for troubleshooting system detected or stop errors. The Module Information tool has a Diagnostic Buffer tab containing diagnostic messages from the CPU and a Stacks tab which gives access to the blocks, interrupt, and local data stacks. You can access hardware diagnostic screens from the PLC menu of Siemens Manager and take the hardware configuration editor online for graphical troubleshooting of the hardware system. We will now show you how to access the different tools, but separate videos go into detail on how to use them. The first tool we will look at is the Module Information tool. While there are a number of ways to launch it, here is one. In Siemens Manager, highlight the Blocks folder, select the PLC menu, and choose Diagnostic Setting. Then click on Module Information. You can also launch this tool by holding down the Control key plus the D key. In the Module Information tool, the Diagnostic Buffer is a good first choice for troubleshooting. Here you can usually find general information on a system detected error. Click the Stacks tab. The Stacks tab contains the block stack, which shows the calling order of the blocks up to the fault. The I or interrupt stack, which shows the value of all the PLC registers and the status word at the time of the interruption, and the local data or L stack, where you can see the local data values of the organization block that started the call sequence. Stacks is a good choice for more advanced code troubleshooting, where you need to see what values are in the different PLC registers at the time of the fault. But keep in mind that the CPU does have to be in the stop mode to view the Stacks tab. Now let's talk about hardware-related errors. Select the station level of the project. Open the PLC menu again. Choose Diagnostic Setting, but this time choose Hardware Diagnostics. Any stations that have diagnostic information will show in this list. Highlight a station and click the Module Information button to bring up the diagnostics for that station. Alternatively, double-click Hardware to open the Hardware Configuration Editor. Put the Hardware Configuration Editor online to see a graphical representation of where there are faults on the system. While online, double-click a station to bring up its Module Information tool. Some advanced tools which can be used for troubleshooting include the Force Table, which allows you to overwrite input or output values regardless of their real-world state, Enable peripheral outputs, which allows you to communicate with outputs even if the CPU is in stop mode. A breakpoint toolbar where you can set breakpoints and monitor code stepwise in statement list, also called STL. There are videos which show in detail how to use all of the tools mentioned in this video. This concludes Introduction to Errors.
In this video, you'll see how to start and stop the PLC from Siemens Manager. To begin, highlight at the CPU level or below in your Siemens Manager project. Open the PLC menu and choose Diagnostic Setting. Then select Operating Mode. Currently, the PLC is running. To put the PLC in stop mode, click the Stop button. You'll be asked to confirm that you want to go to stop. If you do, click Yes. The CPU is now in stop mode. To place the CPU in run mode, click Warm Restart. Again, you'll be asked to confirm the warm restart. If you want to continue, click Yes. The CPU is now in run mode. Close the dialog. This concludes the video Start and Stop the PLC from Siemens Manager. In this video, you'll see how to start and stop the PLC from Siemens Manager. To begin, highlight at the CPU level or below in your Siemens Manager project. Open the PLC menu and choose Diagnostic Setting. Then select Operating Mode. Currently, the PLC is running. To put the PLC in stop mode, click the Stop button. You'll be asked to confirm that you want to go to stop. If you do, click Yes. The CPU is now in stop mode. To place the CPU in run mode, click Warm Restart. Again, you'll be asked to confirm the warm restart. If you want to continue, click Yes. The CPU is now in run mode. Close the dialog. This concludes the video Start and Stop the PLC from Siemens Manager. This video shows how to perform a CPU memory reset from Siemens Manager. A reset of the S7300 CPU with micro memory card clears the CPU's RAM but does not delete the contents of the card. From your Siemens Manager project, highlight at the CPU level or below. Open the PLC menu and choose Diagnostic Setting. Select Clear Reset. You'll see a message asking you to confirm the memory reset. If you want to continue, click Yes. If the CPU is not already in stop mode, a message will ask you if you want Siemens Manager to set the CPU to stop. Choose Yes. After the memory reset, the dialog closes on its own. The CPU's RAM has been cleared. However, the micro memory card still contains all user data. This concludes resetting the PLC's memory from Siemens Manager. This video shows how to set the PLC's time and date using Siemens Manager. In your Siemens Manager project, highlight at the CPU level or below and select the PLC menu. Choose Diagnostic/Setting and then Set Time of Day. If you wish to manually input the date and time, then uncheck Take from PG/PC box. Now you can input the date and time and click the Apply button. To transfer the PG or PC's time to the CPU, leave the Take from PG PC box checked and click the Apply button. In this example, the CPU is now synchronized with the PG. This concludes the video on setting the PLC's date and time using Siemens Manager. In this video, you will see the Module Information Tools Memory, Scan Cycle Time, and Time System tabs. To open the Module Information tool, highlight the CPU level or below in your Siemens project. Open the PLC menu, select Diagnostic Setting, and choose Module Information. Click on the Memory tab. In the case of the S7300, the CPU's RAM or load memory is the micro memory card or MMC. The max MMC that this CPU can take is 8 megs. The size of the actual MMC is 4 megs. The amount of memory in use is 1 meg, and the free memory is 3 megs. The work or high-speed memory is 393K. The retentive memory, which retains data through a stop to run cycle of the CPU, is 131K. These fields are shown graphically in the assignment section of the window. Click on the Scan Cycle Time tab. This tab shows both graphically and in words the watchdog cycle time, which is 150 milliseconds, the longest scan cycle so far, which is 3 milliseconds, the shortest scan cycle, which is 0 milliseconds, and the current scan cycle, which is 1 millisecond. Click the Time System tab. This tab shows the time and date of the CPU, the clock's resolution, which is 1 millisecond, and availability of a real-time clock, which the CPU has. If time synchronization has been set up, it will show here. And that concludes this video. In this video, you will see the Module Information Tools Performance Data tab. In the Module Information Tools Performance Data tab, the Organization Blocks section shows all the organization blocks that this CPU can run. If an OB is not in this list, this CPU cannot run it. In the System Blocks section, all system function blocks and system functions that this CPU can run are listed. If a library SFB or SFC is not in the list, this CPU cannot run it. In the Address Area section, the number of inputs, outputs, and memory bits, along with their address range, are shown. The number of somatic timers and counters and their address range are also shown. This CPU has 32 kilobytes of local data memory available. The number of possible OBs shown corresponds to the OB list above. The number of functions, function blocks, and data blocks that you can create is shown next. The number of SFBs and SFCs also corresponds to the system blocks list above. This concludes Module Information Performance Data tab.
This video shows how to troubleshoot using the blocks, interrupts, and local data stacks of the CPU. We are currently looking at OB1 in the programming editor. Let's monitor the block. You can see that the CPU has gone to stop. Let's open the Module Information tool. To do this, select the PLC menu. Choose Module Information. Normally, we would go to the Diagnostic Buffer tab first, but since this demonstration revolves around the Stacks tab, then let's click on the Stacks tab. Using the blocks, interrupt, and local data stacks for troubleshooting is probably most valuable for code troubleshooting. Here are some important things to note. First, you can only view the stacks if the CPU is in stop mode. The default view is the block stack. What this shows is the calling order up to the fault interruption. This view shows that OB1 called FB18, FB18 called FC28, FC28 called FC57, and whatever fault occurred is in FC57. You can also see if any data blocks were open during the block calls. Now let's look at the interrupt stack. Click the iStack button. There's a lot of information in the iStack window. For instance, the controlling organization block from which the calling was started is OB1 with priority class 1. FC57 was the interrupted block. Data block 18 was open and is 46 bytes in size. The value that was in accumulator 1, shown in hex, was 4Es in the lower byte. Accumulator 2 did not have a value in it at the time of the interruption. You can also view the accumulators in other display formats, such as decimal or floating point. Address register 1 did not have a value, and address register 2 contained data block 0.0. You can also see the value of each of the bits of the status word. The purpose of this video is not to explain what each of these things mean. You can find information about these through other videos. You can also open the interrupted block FC57 by clicking the Open Block button. Let's close the interrupt stack window. The interrupted block FC57 can be opened from the blocks window as well. Highlight FC57 and click the Open button. FC57 opens. There's only one line of code for this demonstration, so the problem either has to be that data block 1 is not loaded into the CPU, or else there's no word 40 in data block 1. A visit to the Diagnostic Buffer tab will tell you which it is. Now let's highlight OB1 on the Blocks tab. Select the Local Data or LStack button. This window shows the hexadecimal values in the local data stack of OB1. For instance, byte 0 of OB1 has the hex value 11 in it. Close the LStack window and close the Module Information tool. Let's pull down the divider window in OB1. Here in the temp variables of the interface is the local data stack where the values you saw earlier were read from. We saw that byte 0 had a 11 in it, which means that there was an incoming event of event class 1. You can find more information about the local data stack of OB1 and the other OBs from the schematic help on OBs. In conclusion, if you have an error that involves block not downloaded or an address that's outside the range, the diagnostic buffer is sufficient for troubleshooting. If, however, you need to know what values are in the accumulators, address registers, and the status word, then the Stacks tool would be very helpful. Remember that you have to be in stop mode to access the Stacks tool. And that concludes this video. This video shows how to troubleshoot a power module failure on the ET200S station. In the Hardware Configuration Editor, click the Online button to get an online graphical view of the system. The red marks indicate a fault with the CPU and the ET200S station. While online, double-click the CPU to open the Module Information tool. Click on the Diagnostic Buffer tab. There's no relevant information here, so let's go to the Station Diagnostics. Close the CPU Module Information tool. Double-click on the IM151-1 module of the ET200S station. The General tab says that the IM151-1 module is okay, but there is an external error. Let's click on the DP Slave Diagnostics tab. Here you see that slot 1, which contains the power module, is faulty. This could be because power was lost, there's a problem with the terminal module, or a problem with the submodule that's plugged into the terminal module. We will now go to the rack and do a physical inspection. Close the module information tool. It was found that one of the incoming power wires was not solidly connected. The wire was seated properly and the terminal retightened, which fixed the problem. To refresh the online hardware configuration, press the F5 key. The station is now up and running, and that concludes this video. Here you'll see how to troubleshoot a signal module failure on the ET200S station. Placing the hardware configuration online gives you a nice graphical view of the system and helps to identify where problems exist. Click the Online button. There's a fault mark on the CPU and on the interface module IM151-1 of the ET200S family. While online, double-click the CPU to open the Module Information tool. Then click on the Diagnostic Buffer tab. The CPU's diagnostic buffer is a good first place to look when faults occur. Sometimes you will find all the information you need there, other times you'll have to look further. In this case, the information is not helpful. Close the CPU's Module Information tool. Making sure you're still online, double-click the IM151-1 to open its Module Information tool. The General tab says the interface module is okay, but there is an external error. Click the DP Slave Diagnostics tab. Here there is slave-specific diagnostic data. In particular, slot 5 is faulty. Now it's time to have a look at the physical station and see what's wrong. After inspection, it turns out that the submodule had been hit with an object and broken. The wiring terminal module, interestingly, was not damaged. A new submodule was plugged in and the problem fixed. To update the hardware configuration view, press the F5 key. This concludes the video on troubleshooting a signal module failure on the ET200S system.
See how to troubleshoot an analog module channel that has gone outside the normal range. From the Hardware Configuration Editor, click the Online button. When troubleshooting hardware, placing the hardware configuration online is a great place to start. You get a graphical view of the modules and can generally see what area to troubleshoot. From this view, you can see there's a diagnostic with the S7300 CPU and also one with the analog module in slot 7. Let's begin by opening the Module Information tool of the CPU. While online, double-click the CPU. The General window notes that the CPU's error LED is illuminated. However, the CPU is still in the run mode. Click the Diagnostic Buffer tab. Message 1 indicates that there's a problem with or maintenance is needed for a module. The module type is an analog signal module with the input address 304. Channel information available means that you can go to the module itself and find channel or input signal. Level diagnostics at the module or submodule, which is where the fault is. Also, the fault is external, not in the code. Close the CPU's Module Information window. In order to get diagnostics from the analog input module, this feature had to be enabled during hardware configuration and then downloaded. You can learn more about this in Parameterizing Hardware Modules videos. Double-click on the analog input module. You can do this either from the Overview window or the Details window. The General tab shows that a diagnostic interrupt has been detected. Click on the Diagnostic Interrupt tab. The Standard Diagnosis of the Module window shows that there's an external error, a faulty module, and that the error occurred with the channel or incoming signal. The bottom window shows channel-specific diagnostics. In particular, it was channel 0, and the problem is that the analog input signal went above the normal range. If this continues to be a problem, We will want to check the instrument for maintenance, cleaning, and possibly recalibration. The error has now been cleared. Click the Update button. The channel error is now cleared. Close the Analog Input Module Information window. This video demonstrates two ways to use the Siemens Service and Support website. Let's start by opening any internet web browser. One easy way to find the Siemens Service and Support site is to do a search. If your browser suggests names, begin typing Siemens Service and you can pick from the list. The actual address is http://support.automation.siemens.com/us. The site has many helpful offerings. In this video, we will highlight two of them. For the first, let's click in the Product Support Documents search box. Let's look for a firmware update for 315-2 Profinet PROFIBUS CPU. Begin typing 315-2PN and associated product links pop up. The order number 6ES7 315-2EH14-0AB0 matches the actual 315-2 PN/DP CPU in our demo hardware rack, so we will click on this link. When the CPU's product page opens, a firmware update shows under the Update section. Let's click the firmware version link. This takes you to an internet document with information about the firmware version update. Further down the page is a link to the hardware version for our CPU. Click the link. Here's some helpful information, the description, and the micro memory card requirements. And here are instructions for updating the firmware using a Siemens micro memory card. And here are instructions for updating the CPU's firmware with a direct connection online. Further down the page is the downloadable firmware update file. Notice here that a newer file is available, version 3.2.8. Let's download this file. Right-click, choose Save Target As, pick a location to store the file, and click Save. After the download, you'll have the choice to open the folder and access the file. Watch the video updating the CPU's firmware to see this file installed on a 315-2 PN/DP CPU. For the second demonstration, let's do a general search. Click in the search box on the upper right side of the screen, and let's do a search on how to update the hardware catalog in S7 5.5. Press the Enter key or click the search button. The first hit is an FAQ on how to update the Step 7 hardware catalog from version 5.2 and later. Let's click that link. Here are the instructions. Let's just browse, pausing for a moment here and there. To see a demonstration of how to update the Step 7 hardware configuration catalog based on these instructions, watch the video Update Hardware Catalog for Step 7 version 5.5. The purpose of this video was to give you an idea of the usefulness of the Siemens Service and Support website through a couple of demonstrations. Please visit the website for manuals and documents, product updates and downloads, FAQs, technical forums, Ask the Experts, your own personal customizable support, and how-to information. There are also links to technical support, field service, repairs, and more. This concludes the video on Siemens Service and Support.
This video shows how to troubleshoot a module failure online with the diagnostics buffer. In the Hardware Configuration Editor, click the Online button. Looking at the online view shows a graphical representation of the hardware system and where faults are located. This is a great place to begin hardware troubleshooting. The red triangle on the CPU means that a diagnostic interrupt has occurred. You can also see that each of the signal modules have a slash mark through them, meaning that they are not communicating with the CPU. While online, double-click on the CPU to open the Module Information tool. Click on the Diagnostic Buffer tab. The first message says that a stop has occurred because of an I/O access error. FC105 was attempting to access I/O. Internal error means the code initiated the access. Click Message 2 for more information. In the details of the event, the message says there was an I/O access error when reading. An attempt to read the P or peripheral area word access with address 306. Also, the organization block OB122 was called for and was not found. This resulted in a CPU stop. A look in the help file tells you that OB122 is called when a module cannot be read from or written to. Message 5 says there was a parameter assignment error. Click on Message 5. This message says there's a parameter assignment error with slot 7. Slot 7 in this rack is an analog module. The reason for the failure is not yet clear. Let's check on Message 6, which is also a parameter assignment error. This message says there's a problem with the input address 304. Message 7 also says there's a parameter assignment error. Let's click on this message. There's a problem with output address 12. Let's move the module information window to the right so we can see the addresses of the modules. Address 304 and 306 are from the analog input module in slot 7. Output address 12 is from the digital input, digital output module in slot 6. We still cannot determine what has happened. Let's look down the message list for more messages. Click on Message 8, also a parameter assignment error. Message 8 says the input address 12 could not be read. This address also belongs to slot 6, the digital in, digital output module. Select Message 9. Message 9 says the output address 4 could not be read. This address belongs to slot 5, the digital output module. Let's click the down arrow box in the Events window again. Select Message 10. It's still not clear at this point what is happening. Click the down arrow in the Events window again, and let's see if there are any more messages. That's the end of the diagnostic messages. We had a message saying slots 7, 6, and 5 could not be read. This agrees graphically with what we see in the hardware configuration editor, but we still don't know why. Now we're going to have to do a physical check of the modules in the rack. We'll close the diagnostic buffer and go look at the physical rack to see if we can determine what's happened. A look at the physical rack showed that there was no power on the first digital input module in slot 4. It turns out the module had failed due to high heat and vibration. As a result, the modules downstream could not communicate to the CPU. When they could not be read during the image updates and code access, messages were output to the diagnostic buffer. The digital input module has been replaced. To update the hardware configuration online view, select the View menu. Choose Update, or you could press the F5 key. This was a difficult fault to troubleshoot. Sometimes the diagnostic buffer will tell you exactly what's wrong and is easy to troubleshoot. But sometimes it's more challenging and will have to be paired with visual inspection of the hardware system to find the actual fault. In this case, we received messages that slots 5, 6, and 7 could not be read from or written to, but had to go look at the rack to see that it was actually slot 4 that was causing the problem. There was a hint though. Since all the modules had slashes through them, and there was a message from slots 5, 6, and 7, that's an indication that slot 4 might be the problem. This concludes the video on troubleshooting a module failure. This video demonstrates how to troubleshoot a Profinet station failure. From the Hardware Configuration Editor, click the Online button. By taking your station online, you can see graphically where problems are in the system. For instance, the red X on the CPU indicates an error. The ET200S has a slash through it indicating the station is down. The red X on the switch also indicates an error, or could mean the hardware configuration profile does not match the actual switch. Since the other stations have faults, it likely means this station is faulted as a result. Double-click on the CPU to open the Module Information tool. Select the Diagnostics Buffer tab. Message 1 indicates that there's a problem, or maintenance may be necessary. Click on Message 2. Here we see the Profinet I/O station has failed. The diagnostic address of the ET200S is input 2040. This is a system reserved diagnostic address. The I/O system ID is 100, which agrees with the ID on the Profinet line, and the station that has failed is station number 1. Click the Line Down button in the Event Details window. The organization block that was called for is OB86, the rack failure OB. The priority class is 26. This means that OB86 will interrupt almost all other blocks. You can find more information about priority classes in the Step 7 help files on organization blocks. OB86 is in the CPU. Therefore, the CPU is still in the run mode, despite the error. Close the Module Information tool. Now let's take a look at station-level diagnostics to see what we can find out. While still online, double-click on the ET200S station to open its Module Information tool. The general screen indicates that the expected module from the hardware configuration is not available on the rack. Click the I/O Device Diagnostics tab. There's no information here, so let's check the Interface tab. The slash indicates that the module is not communicating or available. In the IP Parameters window, no station address can be found. In the Details window, the conflict is that the device cannot be found. We don't know at this point why the station is down. It could be that the ET200S power supply has failed, the Profinet line has failed, or it could be something else. Let's close the Module Information tool. Let's look at the diagnostics of the switch. While still online, double-click on the switch to open its Module Information tool. On the General tab, we see that a diagnostic interrupt has been detected and that it's an external error, meaning there's a problem with a physical component. There's no information here, so click on the Communication Diagnostics tab. In the Communication Diagnostics window, there's an error at port 5. In the Details section, you can see that a device was connected to the port, but is no longer detected. The reason that the switch knows there was a device connected to port 5 and that it is no longer there is because Profinet topology was set up in the hardware configuration editor and downloaded to the station as part of the project setup. Watch the videos on setting up Profinet topology to learn more about this important feature. Close the Module Information tool. We have seen graphically that the ET200S station is down. The switch confirmed that what was connected to port 5 is no longer there. It's now time to go look at the physical station, see what we can find. After examination, it was discovered that the connector on the Ethernet cable had been broken, and the cable was not securely attached to the ET200S port. The cable was replaced and attached between the station and port 5 of the switch. The station and entire system immediately came back up thanks to OB86 in the processor. To refresh the hardware configuration, click the View menu. Choose Update, or if you prefer, press the F5 key. The hardware configuration now shows that all faults have been cleared. In summary, by taking the station online, we could tell right away that the ET200S station was down by the red slash mark through it. Looking at the CPU's diagnostics buffer and the individual station's diagnostics, we confirmed that the station was indeed down, and that port 5 of the switch lost its partner. We then checked the physical rack to determine the actual cause, which was a failed Profinet cable. And that concludes this video. This video demonstrates how to troubleshoot a data block not loaded fault when the CPU goes to the stop mode. To create the fault, we will download OB1. Turn monitoring on. The PLC has gone to the stop mode. Go to the PLC menu and choose Module Information. Alternatively, you can press and hold the Control key plus the D key. Click on the Diagnostic Buffer tab. Message 1 tells you the CPU has gone to stop. Message 2 tells you a data block is not loaded. Click on Message 2. In the Details section, you can see that the data block not loaded is DB17. What's happened is that when the programming call was made to function block 17 and DB17 was created by the programming editor, we forgot to download DB17. This is an easy mistake to make. When OB1 was downloaded, function block 17 was called for, followed by a call to data block 17. When data block 17 was not found, organization block 121 was called for. When it was not found, the CPU went to stop. Minimize the programming editor. From the projects block folder, locate DB17 and download it. At the CPU, toggle the switch to stop and back to run. You can also place the CPU in run through the PLC menu, diagnostic setting, and operating mode. The fault is fixed and the block can now be monitored. To learn more about troubleshooting when OB121 is loaded in the CPU, watch the video OB121. This concludes the video Troubleshooting a Data Block Not Loaded Fault.
In this video, we will review the functional or non-system detected error category and some of the tools used for troubleshooting them. At the top level, there are basically two categories for errors. Those that the system can detect, sometimes called stop errors, and those that the system cannot detect, called functional errors. System detected errors will usually cause the CPU to go to the stop mode if there's no organization block protection. With functional errors, something doesn't work right, but the system cannot detect what it is, and the CPU does not stop. Let's now talk about functional errors. Some examples of these are logical errors in the programming code. For example, using a normally open contact where a normally closed contact should have been used. Supplying the wrong value to a timer. Writing to an output or memory bit more than once, or wiring mistakes that were made in the field. All of these will cause the system to operate incorrectly, but the PLC is not able to detect the problem. Some tools used for troubleshooting functional errors are the variable table, monitoring code blocks, and the cross-reference tables. You can right-click on the blocks folder to create a variable table, or if there is already one in your project, double-click to open it. In the variable table, you can monitor bits, bytes, words, and double words for inputs, outputs, memories, or data blocks. To monitor a code block, highlight the blocks folder and then double-click on a block. Then turn the monitoring glasses on. To open the cross-reference tables from the programming editor or from Siemens Manager, open the Options menu. Choose Reference Data and Display. You may see a message asking if the reference data should be updated. Choose Yes. By default, a window opens asking you which of the 5 reference tools you want to use. Cross-references shows every address and where it is used in the code. Assignments show what inputs, outputs, memories, timers, and counters are used in the code. Program structure shows block call structure beginning from the organization block down. Unused symbols show symbol names which have been created but are not used in the code. And addresses without symbols shows addresses that are used but do not have symbol names. Select a tool such as cross-references and click OK. There are videos which show in detail how to use all of the tools mentioned in this video. This concludes Introduction to Errors.